Okay, so let's have a look at that. So as we saw over here, I've got 4x squared. That is an example of a polynomial, which looks something like this, where we've got some powers of x. So if we want to differentiate polynomials, it's just a two-step process, really. Step one is to reduce the power by 1. So if I've got n over here, I just take away 1 from that power, and we then need to multiply by the old power. So in our case, if I wanted to differentiate something like this, so my dy over dx would be, let's kind of do this. So I have ax. Now, I used to have n as my power, but if we reduce the power by 1, it will be n minus 1. And I need to multiply by the old power, so it'll be n times all of this. Okay, this looks a bit strange. Let's actually use some numbers here. So previously we had y was equal to 4x squared. So let's take these two rules and apply them. So our differential dy over dx is equal to, well, let's reduce the power by 1. So 4x, the current power is 2, so the new power is 1. And then I need to multiply by the old power. So multiply everything by 2. Right, if we tidy this up, this becomes 8x. So now I know a relationship for how my gradient will be depending on the value of x. Okay, let's have a go at a couple more. So let's differentiate this over here. And as you can see, I've got more than one term here. I've got x cubed, a minus 2x, and a plus 4. But we just take each term by term and apply our rules. So let's look at the first one. Dy over dx is equal to, okay, reduce the power by 1. So x cubed will become x squared. And then we need to multiply by the old power. So 3 times this over here. Let's look at the next term, a minus 2x. Now, minus 2x and that plus 4 actually are special cases. We could apply the same rules here. So if we consider it like this is, if I've just got 2x, it's a bit like saying 2x to the power of 1. So let's reduce the power by 1. So I've got 2x to the 0 if I reduce the power by 1. And I need to multiply by the old power. So 1 times 2x to the 0. Now just be careful here, I had a minus sign, so I still need to write down that minus sign. And this plus 4, again, is a little bit interesting. I could think about this as 4x to the 0, and then reduce the power by 1, so we'd have 4x to the minus 1. But if I multiply by the old power, I'm timesing by 0. Right, what are we left with then? So here we've got 3x squared. Here I've got minus 1 times 2x to the 0. If you remember x to the 0, anything to the power of 0 is just 1. So I've got minus 2 here. And then here, for the last term, I've got 0 times 4x to the minus 1, which is just 0. So I'm left with my gradient function being 3x squared minus 2. Right, another way to look at that, because I think this bit can be a little bit tricky if we're just following our rules, is to have the idea of some special cases. So if we have just a 4x, let's say, y is equal to 4x, if I differentiate this, this looks like the straight line equation. I wonder if you noticed that. Right. I've got a power of 1, 4. We know that the gradient there would just be 4. If we had y is equal to, let's say, just 3, just a constant term, well, then the gradient would be 0. So we've got two special cases here. If we have something x to the power of 1, or just x 2x, 3x, then the differential would just be the number in front of the x. It would just be the coefficient of x. So we can see here that the coefficient of x was minus 2, and the gradient for that part would be minus 2 as well. If I have a constant term, y equals 3, let's say, then the differential would be 0. Because remember, if y equals 3, it's not changing. So for that term, y doesn't change as x changes, so the gradient is 0. So you can see here we've got a 0 from just the 4. Okay, let's look at another example. So here there's two parts to this question. It says, can we differentiate y equals 5x squared minus 4x to the minus 2? And then part B, can we find the gradient when x equals 1? So if we recall, when we differentiate, we find dy over dx, which is our gradient function. Well, let's apply our rules over here. We don't need any special cases because we haven't got just a single power. We haven't got like 3x, and there's no like constant terms. We've got just a power of 2, and here we've got a power of minus 2. Alright, so let's follow our rules, right? So first step, reduce the power by 1. So looking at that first term, I've got a 5x. Instead of a 2, 2 take away 1 is 1. And then I need to multiply by the old power. So 2 times 5x to the 1. Let's look at our second term. I've got 4x to the minus 2. So 4x. Now, the power is minus 2. If I reduce it by 1, I make it more negative. So minus 2 take away 1 becomes minus 3. And I need to multiply by the old power. So I'm multiplying by minus 2. Now I mustn't forget that I still had a minus sign in front of this. So I'm going to put another minus sign over here. Right, let's tidy this up. So this gives me 10x, right? 2 times 5 is 10. X to the 1 is just x. And then here I've got minus, and then minus 2 times 4 gives me a negative 8. So minus 8 x to the minus 3. What's minus 8? Well, that becomes plus 8. So 10x plus 8x to the minus 3. So here, our gradient function, dy over dx, is equal to 10x plus 8x to the minus 3. Perfect. Right, so now we know how the gradient varies as x changes. Now part B says, can we find the gradient when x equals 1? So how can we use this information? Well, if I want to work out the gradient when x equals 1, well, the gradient is my dy over dx. So I just need to substitute in x equals 1. So sub in x equals 1. So our gradient when x equals 1 is going to be 10 times 1 plus 8, 1 to the power of minus 3. So you can use, if you need to use your calculator here, you can do, but we end up with 10 plus 8, so 18. So the gradient when x equals 1 is 18. Right, so we've seen a very quick introduction to how to do differentiation when we have powers of x. Now, in engineering, we don't just have x, we could have different letters. So quite often we'll have something varying with time. So instead of powers of x, we might have powers of t, which we kind of mentioned when we talked about velocity and acceleration, right? It was how velocity was how displacement changed with time. So in terms of notation, velocity is equal to ds over dt. Right? Remember, s is our letter for displacements. Acceleration is how velocity varies with time. So that would be dv dt. Okay, so we'll come back to these two concepts in our next video.